everybody. So in section 6.4, we're going to learn how to graph polar equations, which is really exciting because it has to do with your project. And so I actually wanted to start off by showing you a gallery of polar equations. And so depending on a certain polar equation, you're going to produce a different kind of, um, of graphical representation. And so here are 9 different ones. So again, I'm just gonna go a little bit quickly here. And so the first one is again a spiral, and you could get a spiral by just doing r is equal to theta. And theta has, and in this picture here, theta is greater than or equal to 0. Okay, so if you want a little spiral, you just do r is equal to theta. If you want a circle, all you have to do is r is equal to a cosine of theta. And again, this circle is more working horizontally, and so it's going to expand horizontally. And again, for this to get this circle, your a has to be greater than 0. Another type of circle is r is equal to a sine of theta. And so notice that this one is not on the horizontal axis, it's on the vertical axis. And again, here in this case, a is greater than 0. If you want to get a three leaf rose, you could what you do is you actually multiply your angle theta by 3. And so this is in this picture here, my a is greater than 0. And again, it just depends. You can just play with different values of a to get an idea. If you want a 4-leaf rose, then you're gonna want to work with cosine, your trig function cosine, but your theta here, you want to multiply that by 2. If you want this infinity symbol, the equation here is going to be r squared is equal to a cosine of 2 theta. If you want this this cardioid, the formula here would be r is equal to a times the quantity 1 minus cosine of theta, and in this picture a is greater than 0. To get this this other swirly thing, you can do r is equal to a minus b cosine of theta. And if you do, and again, if you want this little loop-de-loop in the middle, then make sure that b is greater than a, which is greater than 0. But if you don't want that loop-de-loop, then you want to make sure that a is greater than b, which is greater than 0. Okay, so again, this is just a little bit of different ways that you guys can produce different designs for your project later on. Okay, these are, again, if you want a flower, then you're going to focus on this equation. If you want a loop-de-loop inside of a circle, then you're going to focus on this certain equation, r is equal to a minus b cosine of theta. All right, so hopefully this little gallery gives you an idea of different things that you can do for your project. So let's move on how to actually graph this. Okay, so given some r, given some theta, or given some theta here, how do you actually produce these really cool images? And so first of all, we're gonna have to talk about the polar coordinate system. Like, how do you even plot a point? So let's actually talk a little bit about that. And so in order for you to actually plot a point, you're gonna need to use your r, which is your modulus, and an angle, which is again the argument or the direction angle. So pretty much we've been talking about that for most of chapter 6. We've been talking about, all right, well, how do we get a modulus and how do we get an argument given a point? And so here I have a polar graph. Right, on my on my left hand side I have a polar graph, and then on my right hand side I have different points. Okay, and they're in polar coordinates. And again, polar coordinates is r comma theta. So let me write that down. So again, my polar coordinates are going to be r comma theta. And so normally we have x comma r. Normally we have x comma y. Now we're going to have r comma theta. All right. And so the way that you plot points is you first look at your theta, and then you look at your r, your modulus. Then you apply apply R. And so it's a little bit to get the hang of it, because it uh in the polar coordinate system, every single circle here, every single inner circle, um, these rings here, they're all have to do with R. So the first one would be R is equal to 1. The second would be R is equal to 2. The third one is R is equal to 3. And so again, depending on what your modulus is, again, you would pick each of the rings. So again, the first ring would be R is equal to 1. The second one would be R is equal to 2. Then R is equal to 3. R is equal to 4. No matter where it is. Okay, again, so like this whole thing is R is equal to 1. The second one is R is equal to 2. So notice that it's not really negative. The negative is going to play a role in a different way. Okay, so the third one here is R is equal to 3. Okay. The fourth one, let's use some pink here. The fourth one is R is equal to 4. Ah, that looks terrible. Let's try this again. This is R is equal to 4. And then the last one, I'm going to do it in orange. That's R is equal to 5. And of course, you can have R that's greater than 5. But in this image, I'm just going to be working with those. Okay. Maybe I should leave it. Maybe this will be helpful for the example. We'll see. If not, we can always erase it. So we'll see if it helps out. Okay, so let's plot the first point here. The first point says 2 comma 5 pi over 6. And like I said, look at theta first and then apply R. And so here we go. I'm going to do the first one in, maybe I should do them all in black because I have a lot of color going on. And so A here is 5 pi over 6. So I'm going to look for 5 pi over 6 on my coordinate system here. So 5 pi over 6 is in quadrant 2. So here's 5 pi over 6. And my R is 2. So 5 pi over 6 is along this line, and R equals 2 is going to give me a point right there. And so that's my A here. Okay, so that's A there. And I just want to let you guys know that these points are not unique. Okay, so there's other ways to get that same location. So I'll show you guys in a little bit. Okay, let's go to the next one. And so again, let's look at the theta first, at my argument. My argument here is pi. And so I'm going to be at pi. So here's pi. And my r is -3. Again, we only have positive r's, but what's happening is we're going to be on my circle 3 because that's r3. But because it's negative, I'm going to reflect it to the other side. And so again, I was along pi. Here was along pi, and I was along the circle 3 here. The circle 3, which is my green here. But because my r is negative, I'm going to reflect it. And so now my point is going to be this point here. So this is B. Okay. And notice again that these are not unique, because another way to get B is another way here to get B is, again, my let me uh let me see. Another way to get B is by doing my R is 0, and not my R is 0. My R is 3, and my angle here is 0. So notice that these have the same location. So again, they're not unique. Just letting you guys know. Okay, these locations are not unique. You can get the same point by doing different polar coordinates. Okay, so now let's keep trying them, and again, slowly but surely. Okay, so the next one, we have -pi over 2. Okay, well, I know I have them here as positive, but if we go clockwise, we'll get the negative. So -pi over 2 is the same thing as 3 pi over 2. And then my R is 1. And so I'm going to be in the blue, on the blue rim here, in the blue circle here. And so that's going to be C. Okay. And again, another way of finding that location is also by saying 1 comma 3 pi over 2. Okay, so again, just letting you guys know that there's a different ways. The next one is pi over 2. Okay, so that's pi over 2 here. Pi over 2, again, let's look at the theta. So pi over 2, we're here. My r is -1. So I am in this blue circle, but because it's negative, I'm going to reflect it, which means I'm actually going to end up at the same location as C. So C and D are in the same place. Okay, so again, this is the same thing as C, which is 1 comma negative pi over 2. All right, so hopefully you're getting the hang of this. Okay, the next one is 7 pi over 12. So again, let's look for 7 pi over 12. That's in the second quadrant. And so here's 7 pi over 12. And again, my r is not only it's 4, so we are going to be in the pink circle here, but it's negative, so I'm going to reflect it, and it's going to end up being at the same location as 19 pi over 12, 4. So it's going to be, again, I'm going to just, so sometimes it might be maybe a good idea to use a ruler. So maybe here, let's see if how I did want to use this ruler. How do I move this ruler? Okay, it's getting a little bit messy here. Okay, maybe I don't want to use the ruler. Okay, eliminate the ruler. Okay. Oh, oh goodness. Okay, here we go. All right. So maybe I'll just use a line to kind of represent. So here's my line. Okay. So again, this is 7 pi over 12, but since I reflected it, now I'm along 19 pi over 12. And again, I'm still in the same r. R is still 4, except again, I reflected it because it's negative. Okay, so you reflect it if your r is negative. All right. Okay. All right. So here we go. Next one. Okay, so that was E. Last one is pi over 4. So there's pi over 4 in the pi over 4 is in the first quadrant, and again -5, so we're going to be on the r is 5, but it's negative, so we're going to reflect it, and it's now going to be in the third quadrant and at the same location as 5 pi over 4. So this is my A. Oh, I called it A for some reason. Let me change that. This should be F. So this should be F. Oh, so let me change that to F. Okay. It doesn't want to. Here, let me just do it by hand then. So that's gonna be F. All right. Okay. Hopefully that made sense. Yeah, because we're actually gonna we're actually gonna need this in order for us to actually graph polar equations. Okay, we're gonna have to actually find these points and then plot them. So we definitely need this skill. So next thing I want to talk about is how to go from polar coordinates to rectangular coordinates, which again is x and y, and go from x and y to r and theta. And so that's going to be the next thing that we're going to talk about. And so to convert r to theta, so to convert r to theta to rectangular coordinates, so that's the first one. We're taking r and theta and we're writing it in terms of x and y. And so again, that's rectangular coordinates would be x and y, which we're actually really comfortable with. So one of the ways that we can do that is we know that x is equal to r cosine of theta from the previous sections, and we also know that y is equal to r sine of theta. And so again, knowing r and theta, then we can just plug them into those equations. If we want to go the other way, if we want to go from x and y, so go from rectangular coordinates to polar coordinates, Well, we also have used this before. We know that r is defined to equal the square root of 2 plus the square root of x squared plus y squared, and theta would be again the angle in standard position that contains the point x comma y. Okay, so again, it depends if you want to go from r and theta, then you would use the first the you would use let me call this a, and if you want to go from rectangular to polar, then you would use b. Okay. All right, so let's try some examples going back and forth. And so my first example here is asking us to convert 6 comma to 6 r is 6 and my theta is 210 degrees to rectangular coordinates. All right, well, we know that r is 6 and we know that theta is equal to 210 degrees. All right, well, we also know that x is defined to be r cosine of theta, so we can just plug it in. So 6 cosine of 210 degrees, which is just 6 times negative square root of 3 over 2, which is just negative 3 square root of 3. All right, and y is r sine of theta. That r looks kind of funky. And so we get 6 sine of 210 degrees. And so that's 6 times 1/2, which is just going to equal to 3. And so in rectangular coordinates, this point here, 6 comma 210 degrees, would be the same thing as negative 3 square root of 3 comma 3. And so we would plot both of them if we plot both of these, they would be at the same exact location. Again, only that one of them, uses x's and y's. The other one, uses an angle and the radius, or and I guess in this case the modulus, in order for us to find that location. So again, there's two different ways of finding that same location, same point. All right, let's go the other way. So now we have it in rectangular coordinates and we have to write them in polar coordinates. Okay, so here we have my x is 2, my y is negative 2. We know that r is defined to be, again, x squared plus y squared, because again, r here, or modulus, would be our hypotenuse of this right triangle that we could create. And so we have the square root of 2 squared plus negative 2 squared, which is the square root of 4 plus 4, which is the square root of 8, which is just 2 square root of 2. So now a way to find theta, well, there's a couple of different ways. So let's figure out where this actually is. So 2, negative 2, that's going to be in the fourth quadrant. So again, that's in the fourth quadrant. We're looking for this angle here. We're looking for this angle theta. So we could use tangent. We know that tangent, let me stay consistent with the colors here. We know that tangent of theta is equal to x over y. Y over x. And so we get negative 2 over 2 is equal to negative 1. And so we're looking for, okay, what angle in the fourth quadrant gives us tangent of theta, tangent of that angle is equal to negative 1. And so that's going to give us theta is equal to 7 pi over 4. All right, and so 2 comma negative 2 is now 2 square root of 2 comma 7 pi over 4. Again, these are the same location. If you really think about it, again, it's the same thing. Again, 7 pi over 4 is going to put me at the fourth quadrant, slicing it right in the middle. And then 2 square root of 2, again, is the distance from the center to that point. And again, is going to give me the same exact location. Again, one of them is in polar coordinates and the other one is in rectangular coordinates. Okay, and so pretty much the summary of that is an equation with x and y is called a rectangular or Cartesian equation. An equation with r and theta is called a polar equation. So now I'm going to show you guys how to come up with those really cool sketches of those polar equations. Okay, and so in this problem here, we're looking for the sketch. We're going to be sketching the polar equation. 3 is equal to r is equal to 3 times sine of 2 theta. And so if we go back to our gallery really quickly, we have a two. Actually, it's gonna look similar to this 4-leaf rose, but because we're working with sine, it's gonna be rotated a little bit. But it's gonna be, again, it's gonna be similar to this style here. And again, let's see how it works. Again, we're gonna plot a bunch. It's just like working with the Cartesian plane. So if you want to find a graph of something, you can just plug in x values and then get values of y, plot the points, and then come up with the actual graph. So it's the same thing here as well. So we have again, I'm gonna plug in values of theta. So I have a couple here on my instead of x and y is my theta and r table. So I'm going to plug in values of theta into my polar equation, and then I'm going to find values of r. And again, by using that, we're going to actually plot the points on my polar Cartesian plane, and then come up with what the sketch actually looks like. All right, and so for the first one, I'm going to plug in 0 degrees. All right, I made it a little bit bigger so you guys can see everything. So okay, there we go. All right, so let's plug in these values of r. So these values of theta. So we get r is equal to 3 sine of 2 times 0 degrees. And so that's just going to be 3 times sine of 0 degrees. And that's just going to give us 0. And so the first one is going to be, again, and I have them flipped, the first one would be 0, 0 degrees. So this point here is going to be 0, 0 degrees. All right. Now let's plug in 15 degrees, which is going to give us a weird number, a little bit of a weird number. So we have, again, r is equal to 3 sine of, actually it's going to be 2 times 15 degrees, which is going to actually give a sine of 30 degrees, which is something that we're familiar with. And that's just going to give us, if we plug it in the calculator, or again, it's going to give us a number that we're familiar with, but I'm just going to write it in decimal form. That way we can kind of get an idea of where it is. Okay, again, if we leave it in square roots, it's going to be a little bit difficult. The next one, again, is r is equal to 3 times sine of 2 times 30 degrees. And that's going to give us 3 times sine of 60 degrees, which is going to equal to 2.6. So we're going to do that for the rest of this. And so if we keep doing this for the rest of the angles here, we get 3 for 45 degrees, 2.6 for 60 degrees, 0 for 90 degrees, negative 3r is equal to negative 3 for 135, r is equal to 0 for 180 degrees, 3 is r is equal to 3 for theta equal to 25, 0 for 270 degrees, and negative 3 for 215 degrees, and 0 for 360 degrees. All right, so again, if you do the same steps here, you'll get these values. Now, what I want to do first is I want to actually plot them in an R, um, uh, R and theta. So this is going to be my theta. This is going to be my R. So first I want to plot it in this this um, this this weird looking graph, which is r and theta. And again, this is going to help us a little bit of see how the shape is going to start being created here on this Cartesian plane. So I'm going to actually plot all these points in this r theta kind of a graph here, and then I'm going to actually draw it out in my Cartesian plane. And again, it's going to be helpful. I hope it's helpful for you guys too. All right, so let me plot in all of these degrees here. Hopefully I have enough room. And so This is going to be, and again, since my Cartesian plane is in radians, I'm going to turn everything into radians. So let's just hold on a second. All right, so I converted all of our thetas into radians. Now, again, you don't have to do this. If you can go from just looking at the points to graphing it, that's fine. But I just wanted to show you a different way of seeing it. It might make your life a little bit easier. I don't know. But you decide. And so I'm just gonna plot all the points here, and you're gonna be able to see um, how that relates to our Cartesian plane when we actually graph it. So I'm gonna do it in a cool color. Let's do green. And so my first point was again 0, 0. So my theta was 0 and my r was 0. So I'm going to start there. The second point, and again, I'm just going based off this chart here. My second point was 15 degrees, which is pi over 12, and my r was 1.5. Oh, why did I put negatives here? I'm sorry, you guys. These are obviously not negative. These are negative. There we go. Okay. It's late. Sorry about that. And so pi over 12 and then 1.5. So it's going to put us right here. And again, notice that at the beginning, I started doing very small angles, and then I just ended up having a bigger and bigger gap in between them. And again, if you wanted to get a more accurate picture, just end up adding more, include more values of theta. If you don't want it, if you want to kind of get a sketch, and that's what we're doing, we're just doing a sketch, kind of get, an idea of how it's going to look, then, we don't have to use as many angles, as many thetas. And so pi over 6, again, that's so 30 degrees. Pi over 6 was 2.6, so that's going to put us like very close to 3, but not really. So right there. And then pi over 4, which was again 45 degrees, is actually 3. And notice that again, our values oscillate between 3 and -3, which makes sense because we're working with the cosine, with the sine function here, sine function. Um, yeah, this was sine. And so then the next one is 60 degrees, 2.6, which is again pi over 3. And so notice that it's starting to come back down. And then at pi over 2, which is 90 degrees, it's at 0. Okay, so obviously there's other angles in between that are missing, but again, this is just to give us an idea. Okay, and so again, it's gonna start increasing, and then it's gonna go back down, of course, because that's how sine works. Okay, and so I'll show you guys how how this graph relates to the Cartesian plane. And so let's just keep on going. And so at 3 pi over 4, we had -3. So we know that we're going to, and again, obviously there's values in between, but we know that this is going to hit. This is going to, again, go here. Let me draw this a little bit better. So this is going to go down to 3, and of course it's going to keep, it's still a sine curve, so we still have to maintain its shape. And then the next one was pi 0. Okay, so it goes back up. And of course, because sine behaves this way. And then the next thing that we found was 225, and then the r was 3. That's 5 pi over 4. Again, back to the top. And again, don't forget that there's obviously angles in between, but we're not going to plot them. And then 270, 0, so 3 pi over 2 back to 0. And then 315, -3, that's 7 pi over 4, 3 goes back down, and then it stops at 2 pi. So again, that's going to be one rotation around the one rotation here in degree wise, or radian wise. So it goes back up to 2 pi. Okay, so now let's see how that behaves, how that transfers into this Cartesian plane. And so again, my first point was let's go back up here. My theta was 0 degrees, my r was 0. So 0, 0. So that's that point. Okay. Now the next one was 15 degrees, so pi over 12, 1.5. So again, I'm in between loop 1 and loop 2, or circle 1 and circle 2 at pi over 2. So again, remember, we need to know how to plot these polar coordinates. The next one was at 30 degrees, which is pi over 6, and it was 2.6. And so we have a little bit passing the 2. And then 45 degrees, which is pi over 4, and my r was 3, so that's that. So notice that this is part of the first part, so that's the first part here that we drew on this graph. So I'll highlight it in a little bit. The next one was pi over 3, which is 60 degrees, 2.6. So again, it's having that symmetry there. And again, we didn't plug in the theta 5 pi over 12, but if we would have plotted, we would have gotten 1.5. Again, there's symmetry here. Okay, and again, we didn't plot it, but we can again, this is a sketch. We can still sketch this out. So here, I'm gonna connect everything. And again, at 90 degrees, we go back to 0. So we go back to that. And so notice that this first little hump of my sine curve was that first petal. Okay? So you can already tell that again, that this is going to create 4 different petals, because again, we have these 4 different little humps. You know, this my wave is oscillating, is creating these four different these little petals. Again, from when we from the beginning uh, and again, that's having theta equals to so when r is at 0 and then ends at 0, that's going to create a petal. All right, so let's actually see if if that is true. All right, the next one was 135, which is 3 pi over 4, and my r is negative 3. And so that's going to, again, reflect it here. So we have 3 pi over 4, but it's going to be negative 3. And so we're going to be actually at 7 pi over 4, 3. All right. And then we have 180, and then back to 0. And so again, we didn't actually plug in any of the other values in between pi over 2 and pi, except 3 pi over 4. And so we're going to get uh, we're gonna have to kind of estimate what it would look like. And so again, we could use the other the values from the previous petal. So for example, from the previous petal, that means that we're gonna have 2.6. Okay, and again, same, it's based off this curve, and then 2.6 here, and then 1.5, and then 1.5. So again, we could use the first petal to estimate the rest of the petals here. And so that's going to be this part where all my r's are negative. Right? So even though my angles are in the second quadrant, because my r's are negative, they're going to be reflected, which is going to be all my points are going to be in quadrant 4. So hopefully you're getting the hang of this. So the next one here, we have we were at pi comma 0, and then the next one, if we look back up to our chart here, we get 135 comma negative 3. 135 again is 3 pi over 4. Oh, we did that one already. Okay, and so then we're at 5 pi over 4. So anything between pi and 3 pi over 2, notice that all of my r's are positive, and so that means that I'm going to get a petal that's actually going to be in that quadrant. So it's going to be actually in quadrant 3. And so we know that 5 pi over 4, that one's actually 3. R is 3. And so we're going to again use the same r's from the first petal to help us, to guide us, draw a kind of accurate sketch here. 1.5, 1.5. So again, if you don't want to struggle like me, then just plug more values of theta, and that's gonna guide you on that's gonna give you a better sketch. Okay, and again, that's my petal, and then now my angles are between 3 pi over 2 and pi here, and 2 pi, but again my r's are negative. So here, let me do it this way. So again, we're between 3 pi over 2 and 2 pi, but again my r's are negative, so that means that we're going to get we're going to be reflected, so we're going to be working in the second quadrant. And so we know that 7 pi over 4, we get negative 3, which we're just going to reflect it up here. So that's going to be 3 pi over 4 with r equals 3. And then again, we can use the first petal to help us graph the rest of the points. 1.5, 1.5. And so that's going to give us that petal there. Oh, that looks terrible. I'm so sorry. There we go. Let's do this again. Okay, that's a little bit better. And so that's another petal there. All right. So hopefully this helps you, gives you an idea of how to graph these polar equations. Okay. And so again, we could have just gone with our theta and r, just plot in the points and then just follow the points along. So you plug in point, you connect it with the next point, or again you could use this r and theta graph here that can help you as well. Okay, last thing I want to talk about for this section is how to uh, convert equations. So first I told you guys, okay, how to convert a polar coordinate into a rectangular coordinate. Now we're going to be converting equations. Okay, we're going to be converting uh, rectangular equations into polar equations. And so we're going to be able to use different things that we have used in the past. So for example, we know that x squared plus y squared is equal to r squared. And so if we wanted to go from rectangular to polar, we could use this equation. Again, we could use this back and forth. We also know that x is equal to r cosine of theta. We also know that y is equal to r sine of theta. And we can always manipulate these however we want. So for example, if we just wanted to have r by itself, we could do x over cosine of theta is equal to r. Or if we wanted to leave cosine of theta by itself, then we could just do cosine of theta is equal to x over r. So whatever, again, we want to manipulate it just to help us write it in either polar or rectangular. Okay, I just wanted to just know that we could manipulate these equations here. Okay. All right, so let's try these examples. Let's really get our hands a little bit dirty here. And so example 4 says, write an equivalent equation for the polar equation r is equal to 2 cosine of theta. And so pretty much what it's telling us is, okay, well, we know that polar coordinates can be are equivalent to rectangular coordinates. So what we can do is take this polar equation and write it in rectangular form. And so let me write that down just to give you guys that little hint here. So this is, it's also asking you to write equation in rectangular form. All right. And so you can write it in x's and y's, or again, both x's, or it could be in x in terms of x and y, or just x's or just y's. Okay. So again, we want to make sure that our final answer doesn't have r's and it doesn't have thetas. So let me write that down as well. Our answer will not have r's. Oh, will not have r's and thetas. Okay, so again, at the end, we shouldn't have those. Okay, so any ideas here? And so normally when I do this in the classroom, we do a couple of different attempts. And so we could do that if we wanted to do. We could try again. We know that r is defined to be, and again we could write it in terms of again, there's different ways of doing this problem. So for example, again, we have r is equal to 2 cosine of theta. We cannot use any of these converting equations. We would have to manipulate them. So for example, um, if we wanted to use the first, so I'm gonna actually name them. I'm gonna call this A, B, and C. If we wanted to use A, we would actually have to have R squared. I mean, we could totally do that. We could actually either square both sides or multiply both sides by R, and that's gonna give us that R squared. So we could try doing that. So if I multiply both sides by R, so let's do that. So I get R times R is equal to, and again, this is R times 2 cosine of theta, well, we would have r squared is equal to, and again, multiplication is commutative, so we can do 2r cosine of theta. And so we know that r squared is x squared plus y squared is equal to 2. And we know that r times cosine of theta, that's just x by b. And so that's just x squared plus y squared is equal to 2x. And now notice that it's only in terms of x's and y's. There's no more r's and there's no more thetas, and so we would be done here. Okay, so again, we could leave it like this. We could also rewrite it by completing the square so that it has like a format in for some um, for a formula for a circle. But again, this is okay. I'm okay with this for now. Okay. So that this is going to give us a formula for a circle. And so we're going to, and again, r equals to 2 cosine of theta. We look back at the gallery, that is actually a circle. And so it makes sense for us to have a formula for a circle for our equivalent equation. Okay, there again, there's just one way to do it. Another unique way to do it is what we could do is what I was mentioning before. So this is attempt number 1 or option number 1. And again, that doesn't mean it's better or anything. It's just the first one that I came up with. The second option is, again, my students have done this in the past, which I think is really clever as well, is we know that cosine of theta is x over r. And so they have r is equal to 2. And again, cosine of theta is x over r. And so we have r is equal to 2x over r. They multiply both sides by r to again isolate that x. And so it kind of gives us back that same thing. R squared is equal to 2x, and we know that r squared is x squared plus y squared. And so we get the same thing again. Okay, and again, it's just different options. And again, you're not limited to these. You can do whatever you want. Okay, but again, I'm just giving you an intuition on how we would attempt these. So let's try the next example. The next one, again, convert it into, again, rectangular equation. And so again, it's actually very similar. So there's nothing really interesting about this one, actually. So again, we could do both ways, or any of the ways. We could let we know that we know that cosine of theta is equal to x over r, right? And so we get r is equal to 4x over r, and again, we multiply both sides by r, we get r squared is equal to 4x. And so we get x squared plus y squared is equal to 4x. Okay. So let's try something more interesting. So let's try example 6. Last example here. This is the last example. And so for each rectangular equation, write an polar equation. So we're going to go from rectangular to polar. So now we want to make sure that there's no x's and there's no y's. Okay, just in terms of either r or theta. Okay, or both r and theta. Okay, so here we go. Let's try A. Okay, so again, we don't want to have any r's or any thetas. And so let me just remind you of the different conversions that we can use. Or maybe it's just put remember. Sounds weird like that. Remember. And so we have x squared plus y squared is equal to r squared. We also know that we know that x is equal to r cosine of theta, and y is equal to r sine of theta. Okay, so here we go. Well, we could let's actually just plug in. We know what we know what x is and y is. Let's just see what happens. So we have y is equal to r sine of theta, and then x is equal to r cosine of theta. Oh, look at that. It's already just in terms of it's already just in terms of x and y. If we wanted to, we can just have it as r equals something, because remember, notice that all our polar equations have r equals to something. We isolate the r. So let's try doing that. So I'm going to move all the terms with r on one side. So we factor out the r. I get sine of theta minus 3 cosine of theta is equal to negative 2. And so r is equal to negative 2 divided by sine of theta minus 3 cosine of theta. So this line here, y is equal to 3x minus 2, okay, is the same as the polar equation r equals to negative 2 over sine of theta minus 3 cosine of theta. That's pretty cool though, right? That a line, again, we can graph that line by using polar equations. And again, it looks pretty funky here, this polar equation. Let's try this last one, b. Okay, so the last one is x squared. And again, this was my answer for the first one. X squared plus y squared is equal to 9. And so well, this one is actually not that bad. It could be. It could totally be. Like, if, for example, maybe you don't notice that x squared plus y squared is r squared. So, for example, one of the options, so option 1, you again, x squared plus y squared, that's just r squared. So this is going to be r squared is equal to 9. So there you go. That's one. That's one of the ways. Um, another thing that you could do is option 2 is well, we know that x is equal to r cosine of theta, so we could do r cosine of theta squared plus y sine of theta squared is equal to 9. And again, everything's in terms of r and theta, but again, let's see if we can clean this up a little bit. This is going to be, I think I messed up here. That's an r. This is going to be r squared cosine squared of theta, and then this is plus r squared sine squared of theta is equal to 9. And we factor out the r squared, we get cosine squared of theta plus sine squared of theta. But we also know that cosine squared of theta plus sine squared of theta, by the identities, that's just 1, so that's just r squared is equal to 9. So notice that again, we get the same thing. So again, this option number 1 was like so nice. But again, you would have to be able to detect that. And again, you detect that by, again, by doing a lot of problems, by practicing. You start remembering, oh, x squared plus y squared, that's just r squared. And so again, it just takes practice. And of course, if you didn't see that, and if you went for option number 2, again, they're both good options. Just one of them is a little bit of a shortcut. All right. Well, that was it for 6.4, everybody. So see you guys next time.